Hey guys, welcome to video 35. We're going to continue our analysis of the amplifiers we first looked at back in video 31. In the last video, we did a cue point and transient analysis of this amplifier using PSpice, and we found that it gave us really good agreement with our theoretical values that we calculated by hand. Today, we're going to look at the frequency response of this amplifier, in particular its low frequency response, and that's determined by the coupling and bypass capacitors. All right, so if we start at the input side, what we've got is our voltage source driving the input resistance of the amplifier, Rin, through coupling capacitor C1, and this forms a high-pass filter. Okay, what we want to do is ensure that the corner frequency of this filter is at least as low as the lowest frequency we want to amplify. All right, the corner frequency for this filter is FC at the base, let's call it, is equal to 1 over 2 pi Rin times C1. Okay, at the output, we're going to model the amplifier as a voltage-controlled voltage source that's determined by AV times Vin, and since AV is negative, I'll throw a negative sign on here. Okay, it's got an output resistance RO, that's typically the collector resistance. We're going through coupling cap C2, and here's our load resistor RL, and this also forms a high-pass filter. But in this case, we want the Thevenin resistance. If you recall when we discussed loaded filters back a few videos, we're going to deal with RTH, and for this circuit, we called that R prime C, and that was equal to RO in parallel with RL. And the corner frequency for this side, the collector side, is equal to 1 over 2 pi R prime C times C2. All right, and again, we want to ensure that this corner frequency is at least as low as the lowest frequency coming in. Now, finally, when we look at the emitter, what we're concerned about is little re, the dynamic emitter resistance, and C3, and in particular, we want to ensure that X sub C is small compared to little re, so that we've got good voltage gain at these low frequencies, okay? Now, let's collect all this information up, and on the next page, I've got the amplifier redrawn with all of its resistances and capacitances, and let's calculate these values, okay? So starting with the input, we've got 2 times pi times 817 ohms times 10 microfarads, and that gives us a critical frequency for this input high-pass filter of about 19 Hertz. All right, that looks good. If we're going to use this as an audio amplifier, a hi-fi amp, we'd need our response to go down to 20 Hertz, so this looks pretty good. Let's check our collector side. Okay, so we've got 2 times pi times R prime C is 1300 times, again, 10 microfarads. And our output corner frequency is about 12 Hertz. That's even better. So we're looking good so far. Now let's do the emitter, where we've got 2 times pi times Re is 20 ohms times 47 microfarads, and that gives us a corner frequency of about 170 Hertz. That's not quite so good. Okay, this is going to be the limiting factor. Okay, if we wanted to operate down to 20 Hertz, our emitter bypass cap is just not big enough. Okay, so we'd have to use a bigger cap here, maybe 100 microfarads or 220 even, to get this corner frequency down with the others. But this might be good enough for some applications, so let's just roll with it. And if I plot the Bode plot for this response, here's what we get. Okay, let me drag this back over so we can look at everything all together, okay? And notice that in the pass band, the gain of the amplifier is about 40 dB, and if we lower our frequency down when we hit about 170 Hertz, the gain starts to roll off at 20 dB per decade. When we hit the next corner frequency, 19 Hertz, it starts rolling off at 40 dB per decade. Then finally around 10 Hertz or 12 Hertz, it's rolling off at 60 dB per decade. But the one that matters most is the first one that we hit, and that's the emitter bypass limit here. So we'd probably want to make C3 larger to move this corner over further. Okay, but that's what we've got, and now we're going to analyze the amplifier and use PSpice to see how accurate this prediction was. Okay, so let's call up PSpice now, and we're going to open the circuit that we looked at. We saved it under the name CEAMP1, and there it is. Okay, now we don't want CEAMP01. That was something I did back in 2009. So here's the one from the previous video, and that should look familiar to everybody. What we're going to do at this point, since we've already done the transient analysis, is we're going to set up an AC sweep. Okay, so we'll hit Analysis, Setup, and we turn on the AC sweep. Let's see, starting frequency of 1 Hertz, that's good, and we'll end at 1 megahertz, that's sufficient. But we want to sweep over decades, so let's turn that option down to decades and hit OK, and then we'll close this. And now what voltage are we sweeping? Well, obviously it's V in, but it's not the amplitude. We used 10 millivolts for that. That applies to the transient analysis. When we're doing an AC sweep, the AC voltage is the voltage that's applied to the amplifier. Okay, now I set it to 1 volt, and normally that would saturate this amplifier like crazy. It would cause it to clip like crazy, but the AC sweep assumes that the amplifier is linear regardless of the voltages you're driving it with, so this is not going to cause a problem. AC sweep uses the small signal model for the amplifier, and it assumes that it works regardless of signal amplitude. Okay, so we're good. We're using 1 volt for our AC sweep, and let's just go ahead and hit Analysis, Simulate. PSpice is crunching the numbers, and now here is probe, and we've got our choice between transient and AC analysis. We're going to choose AC this time, and here's our frequency axis extending from 1 Hertz to 1 megahertz. And what we want to look at is VRL2, that is the voltage at node 2 of RL. All right, so I hit Trace, Add Trace. Let's get rid of these currents, and let's find VRL2, and there we go. Now we also want to look at this in decibels, so let me double click on its label here and insert dB, and there is our Bode plot for the frequency response for this amplifier. Okay, now I'm going to turn on my cursors, and I'm going to drag one out here into the pass band, and we see that let's see, what is our gain? About 39.7 dB. All right, now what I'm going to do is use a second cursor and drag it out to find the corner, and that's where this difference will equal minus 3 dB. So let me start dragging that, and you'll see we're right now about negative 1.1 dB. Keep going, negative 1.8, 2.3, 5, 7, 8, and right about there we're at minus 3 dB, and the frequency is about 256 Hertz. All right, now we were assuming that based on our calculations the gain would roll off at about 170 Hertz, but PSpice is telling us it's actually happening at 256 Hertz. So it's a little higher. It's up around maybe around here somewhere. On this graph it's not that far off, but it's around 260 some Hertz. Now what is accounting for the difference? Well, we're assuming that these three filters are totally independent of one another, but in reality, they're all interacting in this circuit. So they're all affecting each other, and it's not as simple as I'm indicating here. And what it's boiling down to is that our response rolls off a little sooner than what we'd predict, but it's not too bad. Okay, our corner frequency is 256 hertz. Now, if we go a little further, you'll notice down here around 10 hertz, the slope gets a little steeper. Okay, we're rolling off at a higher rate down here, and that's to be expected because we have these other corners clustered together right here as well. So it looks like PSpice is giving us a pretty good correlation with what we expected to get. All right, and that's very encouraging. It means all the work we've done to derive these equations and all of this stuff is actually valid, okay? So that should be reassuring. Now, let's go down and look at the next amplifier that we used in video 31, and that was this common emitter with a bipolar power supply and partial emitter bypass, okay? Now, I've already got all of our results of our manual analysis here, and we'll refer to this as necessary, but what I'm going to do is call up the PSpice version of this amplifier. I've already drawn it, so I don't have to torture you by drawing it here. We'll just open it, and I called that file CE amp2. Okay, and here it is. Now notice it looks pretty much exactly like the amplifier in the presentation. Okay, so again, I like the way PSpice lets me draw schematics. It's very nice. All right, let's set up our analysis here. We're going to do a transient analysis first, and okay, we're going to run it for 5 milliseconds, and we're going to use a 10 microsecond step ceiling so we get a nice smooth oscilloscope waveform out of this thing. Okay, our input voltage, whoops, let's close this. Our input voltage is set for 1 kilohertz, 10 millivolts peak. And let's go ahead and simulate this thing. And it's crunching. All right, we don't need probe right now. Let's just take a look at our DC values. We expect to get 2 milliamps collector current, around 8 volts for VCE, and -5, -12.3, and -13 for our collector base and emitter voltages. Let's see what PSpice tells us. All right, PSpice says we've got -4.7. At the collector, we're looking for -5. That's good. Our base should be -12.33. We predicted -12.3. Again, a good correlation. And PSpice says our emitter is at -13.01, and we predicted -13. So PSpice agrees with us pretty well. And finally, PSpice says our collector current should be about 1.97, and we estimated it as 2. So everything looks good so far. PSpice has vindicated our DC analysis. All right, now let's take a look at our output voltage waveform. Okay, that's going to be this node 2 of RL. So we're going to hit trace, add, and we want, let's get rid of these currents. VRL2, here we go. All right, now once the amplifier settles into its steady state, it looks like we've got an amplitude of about 1.3 volts peak coming out with a 10 millivolt input. So that gives us a voltage gain of 130. And actually it's inverting again, right? Because we have a positive sign coming in, negative sign coming out. But our gain, according to PSpice, is -130. All right, we predicted 103, -103, so that's pretty good. It's actually better than what we predicted. That's about 40 dB, by the way. All right, so everything looks good here. Let's see what the clipping level is for our amplifier. We predicted 6.2 volts on the positive clipping and -8 for the negative clipping levels. So let's see what we get. Okay, we're going to set our input amplitude to something that will guarantee clipping. Let's say 100 millivolts. 100 millivolts. Okay, and let's rerun our analysis. and let's see what our output waveform looks like. So we hit add trace, VRL2, and there we go. So we see we're getting some pretty hard clipping on the negative going portion of the waveform, but softer clipping on the top, okay? And that's normal for this kind of amplifier. We're going to talk a lot more about this kind of clipping and this distortion later on. It's going to be very important to us. But for right now, let's just take a look and see what our clipping levels are. Here, our negative clipping level is about negative 8.1 volts. We predicted negative 8, so that's pretty good. And our positive clipping level is about 6.5 volts. We predicted 6.2, so that's again pretty good correlation between our theoretical values and what PSpice tells us. So again, that should make you feel better about going to all the trouble of learning to do this stuff. It actually works. All right, now let's determine the frequency response of this amplifier. So coming down here, I've redrawn the amplifier and we can see the input high pass filter. It's got a corner frequency of 11 Hertz. The output high pass has a corner frequency of 5 Hertz, and our emitter bypass, actually partial bypass, should have a corner frequency of about 113 Hertz. The Bode plot looks something like this. At 100 Hertz, we're rolling off at 20 dB per decade. At 10 Hertz, we're rolling off at 40. And around 5 Hertz, we're dropping off at 60 dB. All right, let's see if PSpice agrees with this. Okay, so let's rerun our analysis. Okay, we'll set it up for an AC sweep, decades from 1 Hertz to 1 megahertz. That looks good. Let's close it and simulate. All right, now we've got to choose. Let's take our AC analysis, and notice we go from 1 Hertz to 1 megahertz. We will add our output voltage waveform. That's VRL2. And there we go. Again, we want it in decibels, so let's insert our dB notation here. Oops, and there we go. All right, let me turn on my cursors. We've got a passband gain of about 50 dB. Okay, and or I'm sorry, about what? Not 50, 42 dB. Sorry about that. So we've got a gain of 42 dB. We were calling it 40. That's pretty close. Let's see where our 3 dB corner frequency is. Okay, so we're looking for this number to drop to minus 3 dB as I drag my cursor. So here we go. And minus 2, close. Let's see. There we are, minus 3 dB. And our frequency is about 143 Hertz. All right, we were looking for 113. So again, our estimate that we calculated was a little bit optimistic. Okay, and that's because of the interaction we're not accounting for. But it's close enough. All right, and we notice as we move over in frequency that we get a little bit of a transition here around 10 Hertz. That makes sense based on FC at the base of 11 Hertz and the collector of 5 Hertz. So our roll-off rate starts to increase here, and things correlate pretty well with our approximate Bode plot based on these numbers. All right, now you may be wondering, what about the high frequency response of this amplifier? Okay, well, that's primarily going to be determined by the construction techniques you use to build this. All right, PSpice assumes that our construction is perfect and the limiting factor is going to be the transistor. So PSpice would give us a high corner frequency up into the probably tens of megahertz for this transistor. In reality, if you prototype this circuit and you had wires hanging out all over the place, you'd probably be lucky to get a high frequency limit of about 1 megahertz. If you built a PC board and paid attention to layout and stuff, then your high frequency response would approach the PSpice value. And just for the heck of it, let's set up our analysis to see what the upper limit is for this. Okay, so we hit setup, and let's instead of ending our sweep at 1 megahertz, let's take it up to 100 megahertz, okay? That should take us to the high limit of operation for this transistor, and let's go ahead and see what we come up with. All right, we want the AC analysis. We're going to add our output voltage trace. Okay, let's turn it into decibels, and there we go. Okay, so we can see that this amplifier has relatively flat gain from around 100 hertz up to maybe 10 megahertz or so. Okay, we can figure out exactly what it is by, again, looking for a 3 dB drop as we go up. And let's see, there's 1, 2, 3 dB is occurring at about 20 megahertz. Okay, so this amplifier ideally should operate well from around 100 hertz all the way up to 20 megahertz. Again, PSpice is assuming that we built this thing perfectly, and the limiting factor is the transistor itself. In reality, our wiring technique is probably going to cause the corner to be back around here somewhere. All right, so there's another excursion into the land of simulations of these circuits. We'll come back to PSpice again later on, but I think in the next video we're going to take a look at different amplifier classifications, and I will see you in the next video.